Hi, my name is John McCready and welcome to this webinar on how you can reuse simulation methods to accelerate your virtual testing. Let's start by setting the scene to help position these simulation physics methods in our minds as to what they are and how they fit within our simulation tools. The Desktop SOLIDWORKS simulation portfolio provides solutions for virtual testing. These offer competitive simulation tools for the designer right up to the advanced user. All these tools are available on desktop and are known within our community for their capability and usability in terms of user experience. Capability scales depending on choice of the solution, from standard into professional and up to premium for those more difficult problems. So those cover structural. What about specialist domains? Well, there are bespoke solutions for those, for plastics and for fluid flow. And all of these simulation tools are all integrated within the known desktop SOLIDWORKS environment. Now, what if we want to extend beyond what we can do in the desktop into more complex problems? Well, this is where we look at 3D Experience Works Simulia. It's a collection of designer to expert simulation roles that harness Dassault brand technology to enhance the reach and capability of our overall SOLIDWORKS simulation portfolio. These Simulia simulation roles are packaged with apps, delivering a suite of tools to manage, solve, and assess a range of simple to complex, linear and nonlinear problems. Simulia technology in the cloud really helps us extend our reach beyond when users need it. The 3D Experience platform in the cloud is a business platform. It offers an integrated data management, providing a single source of truth to ensure greater traceability. And with its integrated technologies from multiple domains across Dassault Systèmes, it provides solutions for simulation, design, manufacturing, and business intelligence, to name a few, all in a consistent user interface. It's also built on the philosophy of secure access, where we have ownership of tasks. We know who logged in, who created content, who last ran content, and when it was modified. We also have user levels for when you access the platform, which affords a level of IP control so that we let people access the content that we want them to access, when we want them to access it. It's also based in the cloud, so it's mobile. So in terms of simulation results, you can access them when you're on the go and share them with your clients or contractors with live results rather than just a simulation report. Another nice feature of being based in the cloud is that we have scalable hardware at our fingertips. So if we have an analysis that is too large or we want to run it faster to meet a deadline, we can access up to 144 cores per simulation. We also have some agility with the 3D Experience platform in terms of licensing, offering quarterly and annual solutions for our roles. Access to these roles can be scaled as and when you need them on a project-by-project basis. Got a project for 3 months? Scale up to the higher capability role. Don't have a project for the next 3 months? Scale down. Regardless of the simulation solution you choose, however, be it on or off the platform, from SOLIDWORKS, Dassault Systèmes, or elsewhere, there's always common simulation considerations that can be overlooked. One of these challenges is how you effectively train your users, using either traditional approaches like live courses or online tools for self-development, or perhaps with in-house or external mentoring. The idea is to upskill your new users as quickly as possible so that they're working on live production work. The second simulation challenge is how you capture your best practice within your company or within your industry for how you use those tools, how you learn from your experience in virtual testing, and whether or not you create these validated methods that you've found that get you to the answer in the quickest and most accurate way. And that also affords a level of traceability. So it's always good to capture how you get somewhere, the journey. And that allows you to react to market quicker because you'll know, I've done that problem before, I know the method. But it also allows you quality control because of those validated methods. You know that you've done it in the past, so if something looks untoward, it's usually easier to find out why. And the last challenge we'll talk about today is democratization. How do we do more simulation-driven product development? How do we reuse these validated methods that we capture in order to guide new or less experienced users to do more virtual testing and do it effectively? And how do we do that easily to allow our experts, our simulation experts, to focus on new, more complex problems and keep them happy? How do we maximize your available manpower and skill? Well, one way to do this is use physics methods. And that's what we're going to talk about today. So what are physics methods? Well, in this context, they're virtual testing best practices, reusable best practices. And they can be related to modeling preparation, in other words, how you represent what you're simulating. Is it in 3D? Have you simplified it to 2D? Or perhaps 1D beams? How have you meshed it? Have you used particular element shapes or element sizes? And how have you loaded it during the scenario and its analysis? What loads, what restraints are on it, and why have you chosen those particular loads or restraints? And also, how do you interrogate your results? What output is required and in what format? Now, these virtual testing best practices could cover one of these areas or domains, or more likely, it's a mix of all of the above, or a workflow to quickly recreate simulations that you've done before. Simulia rules cover a range of problem domains: structural, flow, plastics, and more. You conceptualize your physics methods and how they'll be used as you simulate day to day. In other words, finding the best method to solve your simulation problem, whether it be enabling others on how to best use the tools for your simulation requirements within your organization, or maybe their methods simply to show people how to quickly complete a drop test of a can. There actually already are standard physics methods embedded within these roles on the platform in a virtual assistant, which is used to help guide new users on how to build these simulations. However, everyone has their own methods and processes they follow to react to simulation demands quickly, such as using certain features, using tools in a particular way, and in a particular order. And all of that is your physics method. And where do you currently keep that data of your methods? As documents, specifications, archive models, or the old-fashioned way, in your head? And how well do those stored solutions react to change? Someone retires, where does the new hire begin? Simulation requirements change. How difficult is it to change a specification? How do you improve something that's in your head? How does somebody improve on something that's in your head? And also, how accessible are those solutions? If they're not in your head, are they document-based? Are they video libraries? And are they shared somewhere? And how? How hard are they to find? Wouldn't it be great if there was a way to take this knowledge and create physics methods that are integrated with our simulation solutions that we can manage, allowing us to apply validated business practices to our simulation, embed complex simulation concepts into a set of distinct ordered actions, automate standard repetitive tasks to facilitate easier and quicker simulation setup, and provide user assistance based on the current context, the problem you're looking at, not a general problem, and help troubleshoot in your commonly run simulations to help you respond quicker to problems. So let's talk about how we create these physics methods on the 3DEXPERIENCE platform with the Simulia roles. Physics methods are created by generating XML files. The first of which you want to look at is an index. This allows you to categorize your physics methods. In other words, you may have physics methods for training, you may have physics methods that are under development, and then you'll have your physics methods that you're using in production. Once you've generated your index, you can build your physics method. And the first thing you'll want to think about is the sequence of operations, the sequence of actions that you must take in order to fulfill that method, if it's built in a simulation, for example. In some cases, some actions have to follow others because they're prerequisites. In other cases, they're interchangeable. In this case, you can see that we've highlighted the material application and model simplification can be switched around in this particular sequence of actions. Either way, we come to the same solution. And another nice feature of your sequence of actions within your physics method are these little glyphs, these little color glyphs you can see on the left-hand side. And what these do is they let you know whether or not the commands you have beneath these actions, the tools you use, are required, whether or not features are optional, or whether or not some tools are unavailable until you complete some earlier actions. For example, we can't examine the drop until we prepare the drop and execute the drop. And once you've nailed down your sequence of actions, you can actually start to define what those actions look like and what commands they will use and what descriptions they will have. So how do we define these actions? Well, what we need to do is we need to tell our physics method what tools we're going to access. Are we going to access them in bulk or just a subset of tools from various apps? And again, we do this by generating our physics method XML, and we use our documentation and a table to work out which tools we actually want to use. And as we build these actions, we can also define some descriptions as to what the actions will entail to help guide our users, and we can also add images to help them work out where these features must be created. So we have our users performing these actions within our method, meshing or whatever it might be. But now we have to give them those tools or present them to them. And we do that through commands. So in this case, we might want them to use a particular meshing algorithm to create tetrahedron meshes, or we may want them to use an automatic meshing technique. Either way, whether we provide the user with a suite of tools or a select subset of tools, we're able to give further information as to how to use those in the description. And if more guidance is required, we can build on that. We can build on the information we give in the actions, and we can build on the information we give in the command descriptors with what's known as these expanders. Expanders within the physics method are essentially containers for information. They can contain more guidance as to how to create a feature or to do some modeling within your physics method to guide the user, or they could be there to help someone troubleshoot with some general guidance, or it could be with bespoke guidance as into how to deal with an error that people know comes up with a very particular piece of geometry or a particular problem. And this can help build that understanding with the users and help increase their knowledge of how to do simulation. So now that we've had a high-level overview of how we generate these physics methods, let's talk about the more important thing. How do we actually share those methods? There are two ways to store and share your physics methods. There's a file-based approach and a managed approach. File-based is recommended more for prototyping, but can be used to share, and all files reside off the platform, but are referenced by your methods. The managed approach leans more on the platform, uploading more content to the platform to increase your traceability. But either method still allows sharing, so consumers can still access your methods to reuse them. So let's talk about how we reuse these methods, and let's do it in the context of an example. And we'll take an explicit drop test method that I've created. The drop test method is accessed by going to their 3D Compass and the Physics Methods Reuse app. And once we access this app, we'll notice that we have our assistant on the right that will take us through the actions we need to perform in order to create this drop test. The first action, what are we going to drop? And this is where I've packaged the commands to perform meshing. But for new users, they may not know, how do I use these tools? So we can provide that expanded help. And we can put in images, we can put in text, and we can add as much information as we want. But there will always be the case that sometimes text and images just aren't enough. It's sometimes more useful to give someone some video content to help them work out how to navigate the environment or navigate your model if it's a large model. In those cases, you can do that. You can directly link videos and access them from within your assistant. So the user here is able to see what operations did I perform to complete that action, and what was the result? What did it look like? How did I generate the mesh? So you could envision there being a lot of these videos for each action, and they could be in place of these expanders, these text and images. You could have videos in here, a video library of how you perform these methods. So the user here has already looked at that video, worked out what they need to do, what settings they need to select, and they've worked through that action. And you'll notice that we have our little glyphs here within our actions. We have our little tick to say that we have said what we're dropping, but you'll notice we've got that little exclamation mark. We've got an error. What does that mean? So I've done this on purpose to show how we can incorporate some troubleshooting. So in this case, the error is caused by the way in which I've generated the mesh. I've done it on purpose to show that we can actually fix it. So the user here is using that troubleshooting method I've detailed to fix that problem. Now, Another thing they could do here is they could feed back to me whether or not to improve the method, to remove the error entirely, which is what I would do. And that's quite easy to do. So once the users essentially define what their drop diners are going to be made of, they can start to think about moving on. Is there any way they can simplify their model? Are they really interested in seeing the deformation of the platform, or are they more interested in seeing what happens to the block? So what they could do is they could create a rigid body or treat the platform as rigid. It's not going to bend, and that'll help speed up your analysis. But you'll also notice that the glyph for that action is optional. You don't have to add a rigid body. You don't have to add connections. So now that they've done that, they can think about actually preparing their drop test. What's going to happen during their analysis? So here you can see they define how long will the drop test take. How long is this item falling, or how long will it bounce for? The next thing they'll want to think about is what's the gravity load, what is the direction, is it in a local or global coordinate system? So depending on how you're working here, again, you can add more help. And you'll also notice that I've got the commands in here, but I've renamed them and I've given them different descriptions. Rather than saying this is an initial velocity, I've called it what speed was it going, to make it a little bit less confusing for newer users as to what each tool does. So the user can move through their actions. They define what that initial velocity is from a 2 meter drop. So rather than seeing it drop for 2 meters and not impact anything, they've started with it close to that platform. But we don't want to see the platform wing away. So in this case, we're going to clamp it so it sits still. And hopefully we'll be able to see this block bounce away when we see the results. The next thing is to find whether or not contact occurs. Right now, that block will go right through that part. So we want to tell it that no, things will contact. And when they do, there is going to be friction. The method we have chosen here to define this contact is general contact. This allows you to very quickly set up a contact relationship. We've selected our friction and we've specified our contact. That fast. We've just basically said anything can contact anything at any time. If you want to learn a little bit more about how we could improve performance by refining that contact, there's information within there. With our drop test configured, we're now ready to drop. We can perform some last minute checks to confirm that we've put values in our loads and our restraints have supports, and we can also perform some pre-processing checks to confirm whether our connections are valid and our contact relationships are good. And then once that's completed, we can have a look at any warnings we may have, and if anything needs action, we can action it. If not, we can continue to resolve. Simulations on the 3DEXPERIENCE platform can be solved in a number of ways. They can be solved on the machine in question, or they can be solved on the cloud. So the user can decide whether or not to solve locally and lock their session to use all their local compute, or they can decide to run their simulation in the background so they can continue to make other simulations while that one solves on their desktop. If, however, they have a larger simulation or they need results faster, they can harness the cloud compute that we mentioned earlier to get up to 144 cores per simulation. And this allows them to react to demands much faster and have more simulations running concurrently. So once that completes, they can visualize their drop, they can retrieve all the results they need, and they can share their results either in a traditional simulation report or live through the browser with some lightweight results visualization. And they can also send those results into a community for others to comment and collaborate on. So now that we've seen how we can reuse a physics method, it should be becoming obvious as to why they could be useful to democratize simulation, to quickly repeat similar problems with a guided approach, helping you troubleshoot and helping you build your features quickly and effectively to react to market demands. And they're useful not just for beginners or less experienced users, but also for experts, particularly when they're trying to remind themselves of how they accomplished difficult, complex simulations in the past, which are perhaps not as simplistic as one part or two parts, but perhaps a car smacking into a panel in a side crash test. But being able to provide these physics methods to users is not just a one-shot fire and forget affair. you need to think about how you're going to optimize these physics methods. So how do we improve them? How do we ensure that they are still the best practice, the best way to do something? Well, it's by using them, and using them in lots of different ways until you find out what tools do I actually use the most, which don't I use at all, is there perhaps a better way to do this? And the best way to do that is through collaboration and having as many people as possible use your methods, and ensure that the developer's intended scope for their physics method has been covered, that it creates all the features it needs to, and it gives the required accuracy that it should. But how do our users inform the developer that changes are needed or improvements? So how can we have our users provide feedback to improve these tools? Well, what we can do here is we can leverage out-of-the-box base functionality on the 3D Experience platform known as 3D Swim. This allows us to generate communities and allow users to communicate and collaborate to drive innovation. And what we can do here is we can embed access to that community within our method itself. So they can access the community, which will launch their browser, and this is accessible on the web. And what they can do here is they can create an idea. They can say what functionality they'd like to be added, what improvement they'd like to be made. They can give a description as to what that might be. They can also add context, so they can add more information in the form of videos, images, and they can drop in files if they wished. And what then happens is that the admin or the methods developer themselves can then assess the request, provide feedback themselves, and the community of other users can also like or comment on the requests that are made. So the methods developer can very quickly see which are the most popular improvements among the user base. So we can also see here that there was a previous request to add some functionality, mass scaling in this case, which can help advanced users improve the performance of a simulation if they sacrifice a little bit of accuracy perhaps. So essentially what you would have here is you would have traceability of all the requests that come in for your physics method. You'll be able to see which are the most popular enhancements to make, and that can help you prioritize your workload as a methods developer creating these physics methods. Up until now, we've been looking at how we create a physics method by specifying a sequence of actions with descriptions as to what that actions entail to progress our workflow. We access features to perform these operations through commands, either by allowing access to all the commands of a particular type or a subset in order to retain focus on our destination. But what if we want more capability? What if we want to customize our physics methods? What if we want to reduce the number of clicks to perform operations? Well, we can do that by accessing scripting and including it within our physics method. And by doing this, we're able to consolidate a number of actions or operations into perhaps a single click. We're able to retrieve inputs from a user, such as values that can be used to generate meshes, or it can be used to apply loads to different features automatically based on our script. So we can make these physics methods very intelligent as our skills develop. But knowledge of scripting isn't needed to create physics methods. So why use a physics method? Well, let's recap on the challenges we talked about earlier. We had three main challenges we were looking at. One was the training of users to make them the most effective in the quickest time possible. And we looked at the traditional ways in which that's done with courses and mentoring. The other challenge was ensuring that you were able to easily capture best practice, that IP, that important IP for your company, to learn from experience, to create validated methods, to find the fastest way to get the solution, and to maintain traceability, so if anything goes wrong, you can track back where the mistake occurred and rectify it. And another challenge was democratization. How do you maximize your available simulation manpower and skill? Well, having spoke about physics methods for the last half hour, I'd like to think that with the integrated guidance we can deliver, we can upskill new users quickly. With the methods capture and the collaboration and the tracking of improvements through a community, we can also improve the quality of our methods and continue to drive innovation. And with these best practice methods, these physics methods, we're able to react to market quicker if a similar problem comes in. We don't have to come up with the method again. We don't have to repeat ourselves. And with these validated methods, again, we're maintaining quality. In terms of democratization, we do maximize our available manpower and skill. We have our advanced users creating methods to enable our less experienced simulation users, so that most of the experts' time then can be focused on working the difficult problems, the more interesting problems, and less of the repetitive tasks for them. So hopefully now you can see how conceptualizing physics methods, created physics methods, sharing them and reusing them can be beneficial to speed up your simulation development and accelerate your virtual testing. Thanks very much for attending this webinar today, and I hope you enjoyed it. If you have any questions, please feel free to let us know.